Right, so evaluating definite integral by substitution method 1. Right, so make the substitution. Right, so here we've got some function inside another function. Right, so we've got g of x and it's inside another operation. Right, so u is the g of x part. Du is g prime of x dx. We're going to evaluate the resulting indefinite integral. Right, and then we're going to substitute back, get the results in terms of x, say f of x, and then substitute the limits of the definite integral into f and subtract, getting f of g of x times g prime, evaluated from a to b, will be f of b minus f of a, where f is the antiderivative. Right, so that's method 1. Let's look at a problem using method 1. All right, so here we have the integral of x times x squared plus 2 cubed dx, evaluated from 1 to 2. We're going to use u to u substitution because we have something raised to a power. All right, so right up here, the u is going to be x squared plus 2 du dx equals 2x. Right, we're going to move the dx over, so du equals 2x dx. We don't see a 2. No problem. Divide both sides by 2. We'll just replace half a du, the x dx, with half a du. Right, so this part here is u, and this part here is half a du. We're not changing the integrals, the limits of integration here, so that we can go right to the integrating part. All right, so let's rewrite it first using substitution, and then we'll integrate. We're going to leave the limits off, right, because we're switching to u's. So we can pull the 1/2 in front. So we have 1/2 u cubed du. All right, so now we'll integrate. So that would be 1/2 u to the 4th divided by 4. And then we can simplify that, u to the 4th divided by 8. Now let's substitute back. So the u is x squared. So we have x squared plus 2 to the 4th divided by 8. And we're evaluating that from 1 to 2. All right, so now we'll just substitute the values in. Right, so we have 2 squared plus 2 raised to the 4th power divided by 8 minus 1 squared plus 2 raised to the 4th power divided by 8. 1 is getting lost there. All right, so that would be 4 plus 6. So we've got 6 to the 4th power divided by 8 minus, that's going to be 1 plus 2, so 3 to the 4th power divided by 8. So 6 to the 4th is 1,296 divided by 8 minus 81 divided by 8. And that's going to be 1213 divided by 8. And that's not going to simplify any further than that because 1213 is not an even number. All right, so there we go. All right, and so here, if you don't want to change the limits of integration, no problem, right? Just substitute back and keep the limits. All right, so now in the next problem, let's look at method 2, and I'm going to do a different problem each time rather than both problems twice because the basic integration is the same. All right, so evaluation of a definite integral, again, method 2. So again, we've got a function inside another function raised to a power, inside a radical, etc., and times the derivative of the inside. Here's the steps using method 2. You're again going to make the substitution where u is g of x and du is g prime of x dx. At the same time, you're going to substitute for the limits of integration, noting that when x equals a, u equals g of a. So in other words, whatever whatever x is, whatever the expression, whatever u is, whatever that expression is, you'll substitute the lower limit in and get a new lower limit of integration. You'll substitute the upper limit in and get a new limit of integration. And then you're going to evaluate this new definite integral of fu du from g of a to g of b by using the fundamental theorem of calculus. In other words, right, so we're going to have whatever the integral, whatever we get when we integrate, whatever g of b is, minus whatever g of a is, right, where f equals the antiderivative. All right, so let's take a look at one. All right, so we're using method 2. We're just changing the limits of integration. All right, so u, we got something raised to a power. U is x squared plus 3. The du dx is 2x. No need to worry here. It's going to just multiply both sides by dx. So du is 2x dx. We got everybody covered. This part will be the u. This part will be the du. We simply now need to change the limits of integration. Right? So new limits, because we're using method 2, new limits of integration. Right? So lower limit. If x equals 0, then u equals, since u is x squared plus 3, u equals 0 squared plus 3, which is 3. And then the upper limit, if x equals 1, then u equals 1 squared plus 3, so that's going to be 4. All right, so we're going to change the limits of integration. All right, so instead of 0 to 1, it'll be 3 to 4, and we will not substitute back. All right, so we're going to rewrite our integral. All right, so we have u to the 1/2 power du evaluated from 3 to 4. All right, so now we're going to integrate. So we just add 1, divide by the same thing. So this would be u to the 3/2 divided by 3/2 evaluated from 3 to 4. Let's simplify that. Of course, dividing by 3/2 is the same as multiplying by 2/3. So we have 2u to the 3/2 divided by 3. And now we're going to just substitute the values. And we're evaluating that from 3 to 4. We'll substitute in the limits of integration. Right, so we have 2, and I'm going to rewrite that as a radical when I go to evaluate. Right, so this would be the square root of 4 cubed. Right, it's easier for me to do that. Divided by 3, and then minus 2 times the square root of 3, not a very pretty number, divided by 3. All right, so that's going to give us square root of 4, of course, is 2. 2 cubed is 8, so this is 2 times 8. This is 16/3. And then minus, all right, this isn't very pretty. That will simplify a little bit. I'm just going to double check. There's no mistakes there, unfortunately. No, 0 squared plus 3 is definitely 3. And so we end up with the 3 underneath there. Could be nicer. All right, so this would be 2 times the square root of 3 cubed is 27. Divided by 3, and 27 is 9 times 3, right? So the 3 can come out. So this would be 16/3 minus, so if we factor out the 3, right, because the square root of 9 is 3, this would be 6 times the square root of 3 divided by 3. And we could reduce that. Our final answer, and we're just going to do the exact answer, 16/3 minus 2 square roots of 3. I think later I'll check that using method 1 just to see. If I get the same answer twice, I know it's right. Right? But I'm not going to do it on the tape. If there's a mistake, I'll fix it. Right? But that seems to be our answer. Not pretty, but 16/3 minus 2 square roots of 3. So the advantage when we're asked to when we are also substitute for the limits, we do not have to substitute back to get the integral in terms of x. So that's one nice thing. You don't have to worry about substituting back if you just change the limits of integration. And you see that the computation on getting those new limits is pretty easy. So the definite u integral that we get is equivalent with the original definite x integral, right, so long as we're changing our limits of integration. All right, so now we're just going to go back and forth. Method 1, method 2, method 1, method 2. Right? I'm not doing any of them twice just because I think that's repetitive. They're very similar on the evaluating. In terms of getting the derivative, it's the same. Right? The only thing that's different is just the evaluating. So rather than doing each one twice, I'll use a different method each time. Right? So the u, right, is going to be not the cosine, but inside there, right? We've got a function inside cosine. So the u should be 3x. You might say, well, how do I know it's the 3x and not cosine 3x? If you don't see a sign, then it's not cos. Right? So u is 3x. That means du dx is 3 dx. I don't see a 3. I do see a 2. All right? So we can factor out the 2, or you can call it, just consider it to have a 2 there. You can just think of it as 2 du dx equals 3 dx, because we're going to divide both sides by 3. Right? So even if we, so you can think of it this way. If we factor out the 2 and then we divide by 3, we're going to get 2/3. You can just pluck the 2 with the du, and you'll get your fraction. We're going to, oops, I don't want to have a dx. If I have a 3 dx, I don't need a dx here. 1 dx per person. All right, so we'll divide by 3. So 2/3 du will replace the dx part. All right, so we're keeping the 2, in other words. And so maybe it makes it easier. I don't want to confuse you. Let's not put the 2 there. Let's just factor it out. I think you might find that better. There we go. All right, so now that 2's not there. And that probably is the easiest way to deal with the 2. So now we have 1/3 du equals dx. So in other words, we've already factored the 2 out, so don't worry about him. The cosine 3x, or excuse me, the 3x is going to be represented with the u. And the dx is going to be represented with the 1/3 du. Cosine stays and 2's factored out. So now you can see, you can put the 1/3 in front and see how we got 2/3. So you can either put the 2 right away with the du or just factor it out. And I think maybe if you just factor it out and don't worry about it, it's probably easier. Right? So the 2's in front. Oh, and we had to divide both sides by 3, right? Because we don't have a 3. So 1/3 du equals dx. The 2's already out there. Now it's 2/3. Right? And we're going to be substituting now. So no limits of integration. And we've got cosine u du. All right? So now we can just integrate, and then we'll substitute back, and we'll evaluate. All right? So whose derivative is cosine? That's sine. Right? So this should be 2/3 sine u. We'll replace the u and add in the limits of integration. So this would be, I'll put it right down below here. So this would be 2/3 sine 3x. And we're evaluating that from 0 2 pi 6. All right, so now we'll do the evaluating over here. I'm going to factor the 2/3 out, so otherwise I got to write it twice. So we have sine 3 times pi 6 minus sine 3 times 0. Right, and that's going to be 2/3. We can reduce that to pi halves. So we have 2/3 times sine pi halves minus sine 0. Sine pi halves, right, that's 90 degrees. It's on the y-axis, that's 1. So we've got 2/3 times 1 minus, and sine 0, of course, is 0. So our answer here is 2/3. That was a nice, easy computation. I think this would be easy no matter which way you chose to do this, substituting back or changing the limits of integration. All right, let's look at the next one. This time, changing the limits of integration. And this one is a creative substitution. Hint, 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 hint. All right? That means we got creative and we rewrote things, x's in terms of u's. All right, so, and we can do that if it's to the first power. If I got exponents, and it all goes to pieces. All right, so u is going to be inside the radical there. U is 4 minus x. The derivative would be negative, right? So the derivative of negative x is -1. And then let's just move the dx right over. So negative dx. So du is negative dx. All right, so we've got u. We don't have a negative there, so negative du will be the dx. But we've got that x there. Oh no, there's an x. We don't have everybody represented. Right? You can't just say, okay, I'll throw an x in there with the u's. It doesn't work that way. But if u equals 4 minus x, then u minus 4 equals negative x. And if I divide by -1, negative u plus 4 equals x. So now we can do a replacement here. All right, so 0, never mind. We're changing limits of integration on this one. All right, let's do the replacement and then let's change the limits of integration. All right, so we have x is now negative u plus 4. And the 4 minus x is u to the 1/2. Now, it's all of x times all of the square root, right? So I need parentheses. It's not 4u 1/2, right? It's the whole thing, right? All of x times the u to the 1/2. So now all I've done is we've replaced the x with that. I just got to make sure I use parentheses and distribute here. And then the negatives outside, du. Now, that doesn't look much better than what we had, except I've got 1 term times 2 terms, and the 2 terms are not raised to a power. I can just distribute the u to the 1/2. That's why this works. So negative u times u to the 1/2 is going to be negative u to the 3/2 plus 4u to the 1/2 du. We've got this rewritten now. All right, so you just got to be kind of aware that when you've got a variable, and both variables here are raised to the first power, you can rewrite the one that's got an exponent or got inside a radical, rewrite that one in terms of u, and then you can, once you've got what u is, then you can rewrite the other one. All right, and if there were exponents, then this would not work out. All right, so new limits of integration. I'm glad we are changing the limits of integration on this one, and I don't have to worry about substituting back. All right, so lower limit. All right, so if x equals -5, then u equals, I just plug in the -5. So I've got 4 minus the -5, which makes that 9. If x equals 0, then u equals 4 minus 0, which is 4. Now, if we look at our integral, we have, no, I should have wrote upper here. So lower, and then this one here, oh, well, I can squeeze it in. This one here was upper. I forgot to write upper. All right, so now if you look at our integral, we've got 9 as the lower and 4 as the upper. Now you may not like that, right? Because you've got a bigger number on the bottom and a smaller number on the top. Don't like that? It's okay, you can switch them and then change the sign. So we can get rid of the negative, switch this to 4 as the lower and 9 as the upper, right? And they are equivalent. And then we have negative u to the 3/2 plus 4u to the 1/2 du. All right, now let's integrate, and then we can evaluate. All right, so we'll increase the exponent by 1. This is going to be, and divide by the same thing. So that'd be 5/2. Negative u to the 5/2 power divided by 5/2 plus 4u to the 3/2 power divided by 3/2. That gets evaluated from 4 to 9. The negative is only on the u, right? It is not distributed to the 4, so that the signs are correct there. All right, so now let's rewrite this. So this would be negative 2u divided by 5, and the u is to the 5/2 power. Squeeze that in there. Plus, this would be 2 times 4, so that's 8u to the 3/2 power divided by 3, right? Just multiply by the reciprocal there. And we're evaluating that whole thing, I should put parentheses, from 4 to 9. All right, so we'll just plug those numbers in. Let's see if I can write a little bit smaller. Perhaps if I move this over just a little bit, I'll have space. Okay. All right, so we have, here we are evaluating. All right, so this would be negative 2, and then I'm going to rewrite that as a square root. So the square root of 9 to the 5th power divided by 5 plus, oh boy, squeezing this in isn't going to be easy. I'm just going to move some things around just a little bit. I'm trying not to get out a new page. Let's just move. Come on. Doesn't want to move. All right, there goes the dx. Well, I thought this was a good idea. Now I'm thinking, no, probably not. All right, there's u equals, u over the 4 minus x. Move the du, oops. And move the negative du equals dx. There we go. And then we can move this up. And that up. And ignore the green lines. And then we'll evaluate down here, and it'll actually fit, and I won't have to write it in 2 lines. There we go. All right, now we can squeeze that in. All right, so negative 2 times the square root of 9 to the 5th power divided by 5 plus, now I'm going to put parentheses around that, still got to substitute the 9, plus 8 times the square root of 9 to the 3rd power divided by 3, and then minus, now I plug in the 4's, so negative 2 times the square root of 4 to the 5th power divided by 5 plus 8 times the square root of 4 cubed to the 3rd power. There we go. So now we'll just evaluate. All right, so square root of 9 is 3. 3 to the 5th power, so it's going to be negative 2 times 3 to the 5th power is 243. 81 times 3. Divided by 5 plus, all right, so this is going to be now 8 times the square root of 9, that'd be 3 cubed, that'd be 27, divided by 3, and then take that, and then minus, so this would be negative 2, square root of 4 is 2, 2 to the 5th power is 32, divided by 5, plus square root of 4 is 2, 2 cubed is 8, so this is 8 times 8 divided by 3. All right, so why don't we distribute negatives and combine the fifths together and the thirds together, and then we'll just one time. All right, get a common denominator and add the things together. So that would be 2 times 243. 4, why am I multiplying that? And the calculator, I think I can do 486. I'm doubling, negative 486. Tells you it's time to, it's pretty close to the end of the video. And then plus, we can reduce that, why not? So the 27 divided by 3 would be 9, so this is 72. Minus a negative, this is going to be plus, and that's going to be 64 fifths. And then that's going to be a minus 64 thirds. That's weird how that worked out. Yeah, that's what it is. All right, so let's combine the fifths, and then may as well, it's fine, the 72. We'll have to change everything to a denominator of 15, though, unless something else drops out. So the negative 486 plus 64, that's going to be negative 422. Right? Yes. Fifths. And then minus 64 thirds and 72. Everything's got to have a denominator of 15. All right, so let's change. So we got a common denominator, and then we'll be done with this one. Oops, that's too far. All I wanted to do was a little bit more space because I got one more line. Whoops. Don't pull out my microphone. Oh, I almost stepped on my microphone. That would not be good. And what happened to my little bit of space? All right, no, stay. All right, change all 15s. So that means multiply that 422 by 3. Gives us 1, negative 1,266 fifths, minus, change that to, fifteenths, change that to 15ths, so multiply 64 times 5, and that's going to be 320. And then plus 72 times 15, 1,080, and apparently we're going to be negative. So 1080, we got and then this is going to be negative 506/15. Ta-da. And will not reduce, so. So for a negative, that means more of the area is under the curve than over the, under the x-axis than over the x-axis, because we got negative. All right, and this one is done. And hopefully there was no mistakes. I don't think so. Nope, looks pretty good. Looks pretty good. If there's a computation error, you let me know. I'll fix it. I'm going to end the video here because I've got one. Let's see, I've got how many left? I have 1, 2, 3, 4, 5, about 8. And some of these require some creativity. So I'm going to end here. And then in the next video, we will do a few more. And that's going to be it for numerical integration, but one more video. All right, and then we're going to combine the UDU substitution, as you can see to the side there, with some more techniques. All right, so bye for now.